Properties of integers. The set of integers is denoted with z, and it consists of the numbers 0, 1, -1, 2, -2, and we continue like that indefinitely in both directions. We say that the number 5 divides the number 10 because 10 can be written as 5 times another integer, in this case 2. And obviously 5 doesn't divide 11. We write this like that, doesn't divide 11, because 11 cannot be written as equal to 5 times some integer. We'll use the floor function. For any real number x, the floor of x is denoted this way, and this is just the largest integer less than or equal to x. To get the floor of some real number x, we just round x down to the closest integer. For example, the floor of 2.9 is 2, the floor of negative 3.6 is -4, and this is because negative 3.6 is between -3 and -4. So the closest integer down is -4. Theorem, division algorithm. Let a and b be integers with b positive, then there exists unique integers q and r with the property a is equal to bq plus r, where r is non-negative and strictly less than b. Also, q is equal to the floor of a over b, and r is a minus bq, because we already know q from here. For example, if a is 350 and b is 65, find the quotient and the remainder. We find first 350 over 65. This is approximately, this is 5.38. You just put this in the calculator. It continues, but it is clear that the floor of this number will be 5. So this is the quotient q, and the remainder r will be 350 minus 65 times 5. Put this in the calculator and you'll get 25. So the remainder is 25. And from here, we can write that 350 is equal to 65 times 5 plus 25. So the remainder is as needed, non-negative and strictly less than the divisor 65. Definition: greatest common divisor of two integers a and b is the largest of all common divisors of a and b. We denote it this way: GCD of a, b. For example, the GCD of 5 and 10 is equal to 5, because phi is a common divisor of these two, and because this number 5 is not divisible by any bigger number than this 5, this is the greatest common divisor of 5 and 10. If the GCD of two numbers a and b is 1, we say that they are relatively prime. A and b are relatively prime. And this is an important theorem. The GCD of any two numbers can be written as a linear combination of those two numbers. So there exist integers s and t such that as plus bt is equal to the GCD of a and b. Moreover, the GCD is the smallest positive integer that can be written in this form. The proof of the theorem is given in the book. Here we now show how it follows from the Euclidean algorithm. We show this with an example. Find the GCD of 350 and 65 using the Euclidean algorithm, and then write it in the form 350s plus 65t for appropriate numbers, integer numbers s and t. First, we start the Euclidean algorithm. Divide this by 65. 350 divided by 65. We'll get a quotient q and a remainder of 25, as we know from above. Then the next step is shift the previous divisor, 65, becomes a dividend in the next row. The previous remainder becomes a divisor, and we divide 65 by 25. It goes 2 times, and the remainder is 15. Then shift again, 25 here, 15 here, and divide again. The quotient now is 1, so I don't write factor 1, and the remainder is 10. And we continue this process of shifting and dividing until we get a remainder of 0. 15 divided by 10, the quotient is 1, the remainder is 5. Shift 10 divided by 5 is 2, and the remainder is 0. The remainder of 0 means stop the algorithm. The last non-zero remainder is the GCD. So I get that the GCD of 350 and 65 is 5. Then we start backward substitution to get the linear combination. From here, 5 is 15 minus 10. These remainders here are important numbers. We don't lose important numbers by multiplying them. From the previous equality, we express 10 as 25 minus 15. So instead of 10 over here, we write 25 minus 15. Then we simplify. Distributive law applies here. Negative sign must be distributed. So negative 25 plus 15. And how many 15s we have? One here. So we have 2 times 15 minus 25. So we keep 15 as a factor, and 25, these are important numbers. Then 5 is written this way, as such linear combination. The smaller of the important numbers is 15. We express it from the Euclidean algorithm. So instead of this 15, we'll write what? 65 minus 25 times 2. Then distributive law applies, but 65, we want to keep this number. 25 is also important. So we just write 65 times 2. Don't write 130 instead. Keep 65 as a factor. And then this must be multiplied by 2, but we multiply the number 2. We keep 25 as a factor. 2 times 2 is 4. And then how many 25s we have? Four here and 1 here, so altogether 5. So we collect those two. And finally, this 25 will be replaced with another linear combination. So I copy. Instead of this 25, here we have just 5. Instead of this 25, we'll write 350 minus 65 times 5. And then distributive law applies here, but again, keep 65 and 350 as factors. (350 times 5), and then we have we'll have parentheses here, minus 65. 5 times 5 is 25. So we keep 65 as a factor. And here we have distributive law, so distribute this negative sign. So minus 350 times 5. Negative times negative is positive, so plus 65 times 25. And then we collect how many 65s we have. 2 here, 25 here, so altogether 27. So I write 5 is equal to 350 times negative 5 plus 65 times 2 plus 25, 27. So this is our linear combination. Let's check. Put this in the calculator. The result will be exactly 5. So it is correct. We found the linear combination, and here S is negative 5, T is 27.